In their mission to grasp the first stars and systems that illuminated the universe, space experts are still in obscurity. Be that as it may, they are drawing nearer to illumination one revelation at a time. This is the inconceivable yet certain outcome from phenomenal discoveries by the James Webb Space Telescope, JWST, the $10 billion time machine that just formally concluded its first year of observations. The telescope was designed to capture the faint infrared glow of the universe's earliest luminous objects. Webb's vision has reached back into the first few 100 million years after the Big Bang, allowing it to gather more and better data about infant galaxies than any other facility yet built. Yet, its haul of cosmic baby pictures has proven more abundant than most experts dared to dream. Simply put, candidate galaxies in the early universe are springing up in numbers that defy expectations. Dozens have been observed so far, and that makes scientists go crazy. As Charlotte Mason, an astrophysicist at the University of Copenhagen, said, "We weren't anticipating this." In the weeks and months following JWST's discoveries of surprisingly mature early galaxies, theorists and observers scrambled to make sense of them. Could the flock of unusually large and bright early galaxies be a mirage, perhaps due to flaws in the analysis of the telescope's initial observations? If genuine, could they somehow be explained by standard cosmological models? Or, just maybe, were these the first clues that the universe is more bizarre and complex than even our boldest speculations had assumed? Was the Big Bang Theory wrong? Let's dive deep into how the James Webb Space Telescope has broken our understanding of the universe. To grasp the predicament, let's return to when the universe was believed to have formed after the Big Bang. The infant universe began cooling, and within a few million years, the roiling plasma that filled space settled down. Electrons, protons, and neutrons combined into atoms, mostly neutral hydrogen. Things were quiet and dark for a period of uncertain duration, known as the cosmic dark ages. Then something happened. Most of the material that flew apart after the Big Bang is made of something we can't see, called dark matter. It has exerted a powerful influence over the universe, especially in its early stages. In the standard picture, cold dark matter, a term that implies invisible or slow-moving particles, was flung about the universe. In some areas, its distribution was denser, and in these regions, it began falling into clusters. Visible matter, meaning atoms, gathered around these clusters of dark matter. As the atoms cooled, they eventually condensed, and the first stars were born. These new sources of radiation reionized the neutral hydrogen that filled the universe during the so-called epoch of reionization. Through gravity, larger and more complex structures formed, building a vast cosmic web of galaxies. Meanwhile, everything kept flying apart. The universe has been expanding rapidly ever since. In the 1920s, the astronomer Edwin Hubble figured out that the universe is expanding. In the late 1990s, the Hubble Space Telescope found evidence that this expansion is accelerating. Imagine the universe as a loaf of raisin bread. It starts as a mixture of flour, water, yeast, and raisins. As the yeast begins to ferment, the loaf rises, and the raisins, representing galaxies, are carried farther apart. The Hubble telescope showed that the loaf is rising even faster, with galaxies flying apart at an accelerating rate. This acceleration appears to be driven by the strange energy of space itself, called dark energy, represented by the Greek letter lambda. Plugging values for cold dark matter, normal matter, and radiation into the equations of Albert Einstein's general theory of relativity gives us a model of how the universe evolves, the lambda-CDM model. This model matches nearly all observations of the universe. One way to test this model is by observing very distant galaxies, essentially looking back in time to the first few 100 million years after the Big Bang. The universe was simpler then, and its evolution is easier to compare against predictions. Astronomers first tried to observe the earliest structures using the Hubble telescope. In 1995, over 10 days, Hubble captured 342 exposures of a seemingly empty patch of space in the constellation Ursa Major. Astronomers were astonished by the abundance hidden in the inky blackness. Hubble revealed thousands of galaxies at various distances and stages of evolution, stretching back to earlier times than anyone had expected. In 2016, astronomers discovered one of the most distant galaxies yet, called GNZ11, a faint smudge dated to about 400 million years after the Big Bang. This was shockingly early for a galaxy, but it didn't completely break the lambda CDM model. GNZ11 was small, with just 1% of the Milky Way's mass, and stood as an outlier. Astronomers needed a more powerful telescope to see whether GNZ11 was a fluke or part of a larger population of surprising early galaxies, galaxies that might help determine if we're missing a crucial piece of the lambda CDM puzzle. This is why the James Webb Space Telescope, JWST, was built. Launched as the largest, most powerful observatory ever sent from Earth, JWST was designed to revolutionize our understanding of the universe. Positioned 1.5 million kilometers away from Earth's interference and cooled close to absolute zero by its tennis court-sized sun shield, the telescope carries a giant segmented mirror and exquisitely sensitive instruments. These were designed to reveal details of cosmic dawn never before observed. That promise was fulfilled when, within just weeks of full operation, JWST began to deliver discoveries beyond astronomers' wildest expectations. Most out-of-this-world fantasies it has seen, the universe, amazingly near the beginning of recorded history, examined the airs of exoplanets in remarkable detail and gave shocking new perspectives on universes in our planetary group. However, it's simply getting begun, as Webb's vision arrives back into the initial not many 100 million years after the huge explosion, permitting it to acquire more and better information about infant universes than any other office yet worked. The question isn't anything less than our exceptionally comprehension of how the methodical universe we know rose up out of early-stage disarray. Webb's initial discoveries could revise the initial sections of vast history, which concern not just ages in faraway systems, but also our own presence here in a natural, smooth manner. As JWST scientist Imrit Mitkafayer, a senior consultant for space and exploration at the European Space Office, said, "You build these machines not to affirm the worldview, but to break it. You simply don't know how they will break." Scientists use a version of the Doppler effect to measure the distances of objects. This is comparable to figuring out the location of an ambulance based on its siren. The siren sounds higher in pitch as it draws near and then lower as it moves away. The farther away a system is, the faster it moves away from us, as its light stretches to longer wavelengths and appears redder. The extent of this redshift is expressed as Z, where a given value of Z tells you how long an object's light had to travel to reach us. One of the first papers on JWST data came from Naidu, the MIT space expert, and his associates, whose search algorithm flagged a galaxy that appeared mysteriously bright and untouchably far off. Naidu named it GLAST-Z13, indicating its apparent distance at a redshift of 13, further away than anything seen before. The galaxy's redshift was subsequently downgraded to 12.4, and it was renamed GLAST-Z12. Other cosmologists working on different sets of JWST observations were reporting redshift values from 11 to 20, including one galaxy called Source 1749, or CR2Z71, whose light seems to have left 13.7 billion years ago, only 220 million years after the Big Bang, scarcely a blink of an eye after the beginning of cosmic time itself. These putative detections suggested that the neat story known as LCDM might be incomplete in some way. Galaxies became huge quickly in the early universe. "You don't expect to see massive systems," said Chris Lovell, an astrophysicist at the College of Portsmouth in Britain. In a study published in November, specialists examined programmatic simulations of galaxies governed by the LCDM model and found that JWST's early bright galaxies were significantly heavier than those that formed at the same time in the simulations. Some astronomers and media outlets claimed that JWST was breaking cosmology, but not everyone was convinced. One issue is that LCDM predictions aren't always clear-cut. While dark matter and dark energy are straightforward, visible matter has complex interactions and behaviors, and nobody knows exactly what went down in the first years after the Big Bang. Those turbulent early times must be approximated in computer simulations. The other issue is that it's difficult to know exactly how far away galaxies really are. In the months since the first papers, the ages of some of the claimed high redshift galaxies have been re-evaluated. Some were downgraded to later phases of cosmic evolution, thanks to updated telescope calibrations. JWST 1749, for example, is located in a region of the sky containing a cluster of galaxies whose light was emitted 12.4 billion years ago. Naidu says it's possible the galaxy is part of this cluster, a closer intruder that might be filled with dust, causing it to appear more redshifted than it really is. According to Naidu, JWST 1749 is odd, regardless of how far away it is. It could be a new type of galaxy, a very low-mass, small galaxy that somehow accumulated a lot of dust, which is something we generally don't expect for such distant galaxies. Everyone knew that the most definitive distance estimates would require JWST's full power. JWST not only observes starlight through photometry, measuring brightness, but also through spectroscopy, measuring a light's wavelengths. If a photometric observation is like a picture of a face in a crowd, then a spectroscopic observation is like a DNA test that can reveal a person's family history. Naidu and others who found large early galaxies estimated redshift using brightness-derived measurements, essentially looking at faces in the crowd with a good camera. But that method is far from airtight. At a January meeting of the American Astronomical Society, astronomers joked that maybe 50% of the early galaxies seen with photometry alone would turn out to actually be misestimated. However, in early December, astronomers announced that they had combined the two methods for 4 galaxies. The JWST Advanced Deep Extragalactic Survey, JADES, team looked for galaxies whose infrared light spectrum suddenly cuts off at a critical wavelength known as the Lyman break. This break occurs because hydrogen in the space between galaxies absorbs light. Due to the ongoing expansion of the universe, the ever-expanding raisin-loaf effect, the light from distant galaxies is shifted, so the wavelength of that sudden break shifts too. When a galaxy's light seems to drop off at longer wavelengths, it is farther away. JADES identified spectra with redshifts up to 13.2, meaning the light was emitted 13.2 billion years ago. When the data was downloaded, JADES researchers started going crazy in a shared Slack group. According to Kevin Hain, an astronomer at the College of Arizona, he said, "It was like, wow, oh my God, we did it, we did it, we did it." He said these spectra are just the beginning of what will be a transformative moment for astronomy. Brant Robertson, a JADES cosmologist at the College of California Santa Cruz, says the findings show that the early universe changed quickly in its first billion years, with galaxies growing 10 times faster than they do today. "It's like how a hummingbird is a small creature," he said, "but its heart beats so quickly that it's living a different kind of life than other animals. The heartbeat of these galaxies is happening on a much faster timescale than something like the Milky Way, but were their hearts beating too fast for LCDM to explain?" As astronomers and the public marveled at JWST's images, researchers started working behind the scenes to determine whether the galaxies flickering in our view really defy LCDM or simply help refine the numbers we should plug into its equations. One important but poorly understood number concerns the masses of the earliest galaxies. Cosmologists try to determine their masses to tell whether they match the LCDM predicted timeline of galaxy formation. A galaxy's mass is calculated from its brightness, but Megan Donahue, an astrophysicist at Michigan State College, expresses that, best-case scenario, the connection between mass and brightness is a ballpark estimation based on assumptions gathered from known stars and well-studied galaxies. One key assumption is that stars generally form within a certain statistical range of masses, called the initial mass function, IMF. This IMF parameter is crucial for estimating a galaxy's mass from measurements of its brightness because hot, blue, massive stars produce more light, while most of a galaxy's mass is typically locked in cool, red, small stars. However, it's possible that the IMF was different in the early universe. If so, JWST's early galaxies may not be as heavy as their brightness suggests, they might be bright but light. This possibility causes headaches because changing this fundamental input in the LCDM model could give you almost any answer you want, Somerville said. Confirmation that LCDM can accommodate at least some of JWST's early galaxies arrived the day before Christmas. Astronomers led by Benjamin Keller at the University of Memphis checked a handful of major supercomputer simulations of LCDM galaxies and found that the simulations could produce galaxies as heavy as the 4 that were spectroscopically studied by the JWST team. These 4 are significantly smaller and dimmer than other proposed early galaxies like Glass C12. In the JWST study, all the simulations yielded galaxies the size of the JWST findings at a redshift of 10. One simulation could make such galaxies at a redshift of 13, the same as what JWST saw, and 2 others could build the galaxies at an even higher redshift. None of the JWST galaxies was in conflict with the current LCDM worldview, Keller and Associates reported on the preprint server arcs4.org on December 24. Though they lack the mass to break the dominant cosmological model, the JWST galaxies have other unique qualities. Hinden says their stars seem unpolluted by metals from previously exploded stars. This could mean they are population 3 stars, the eagerly sought first generation of stars to ever ignite, and that they may be contributing to the reionization of the universe. If this is true, JWST has already looked back to the mysterious period when the universe was set on its present course. Despite the big picture finding, stuck scientists remain in a state of flux, continually testing, analyzing, and reinterpreting the data provided by the James Webb Space Telescope, JWST. The telescope's phenomenal capabilities offer a tantalizing glimpse into the earliest moments of cosmic history. However, the complexities of interpreting this data highlight the challenges inherent in unraveling the mysteries of the universe. As researchers delve deeper into the observations yielded by JWST, they confront a host of questions that resist easy answers. The inconsistencies between theoretical models and observational evidence spark debates within the scientific community, driving further investigation and refinement of existing theories. Each new discovery serves as a catalyst for progress, pushing the boundaries of our understanding and inspiring new avenues of inquiry. As scientists continue to sift through the wealth of data provided by JWST, they do so with a sense of humility and awe for the vastness of the universe. Each observation offers a fleeting glimpse into the cosmic tapestry, inviting us to ponder our place within the grand design of existence. And while the journey towards enlightenment may be fraught with challenges and uncertainties, it is ultimately a journey worth undertaking, a venture that promises to broaden our horizons and deepen our appreciation for the wonders of the universe. In this ongoing quest for understanding, collaboration and interdisciplinary exchange play critical roles. Scientists from diverse fields come together to share insights, challenge assumptions, and collectively push the boundaries of knowledge. Through collaborative efforts, researchers can leverage their respective expertise to tackle complex questions and decipher the intricate workings of the universe. Furthermore, the significance of JWST extends beyond the realm of pure scientific inquiry. Its discoveries have the potential to inspire future generations, igniting a sense of wonder and curiosity about the universe. By fostering a deeper appreciation for the beauty and complexity of the cosmos, JWST serves as a catalyst for scientific literacy and public engagement. As we navigate the complexities of cosmic exploration, it is essential to maintain a sense of curiosity, humility, and open-mindedness. The universe has always been, and will continue to be, full of surprises, challenging our preconceived notions and inviting us to explore new frontiers of knowledge. In the end, the journey of discovery fueled by JWST is not just about unraveling the mysteries of the universe, it is about embracing the wonder of existence itself. With each new observation and every new discovery, we inch closer to a deeper understanding of our place in the universe and the profound interconnectedness of all things. And as we peer into the depths of space, we are reminded of the endless possibilities that lie ahead, waiting to be explored and embraced with boundless curiosity and awe.